Good afternoon, my fabulous chemistry students. Video number 2. Today we are going to delve into the phases of matter, something we actually know a little bit about ahead of time from all our early science careers and even this year, right? We need to basically be able to differentiate, though, at the atomic level now, what's the difference between solid, liquids, and gas, and what's really going on, right? But so, do we really need to know any more on that? Well, we actually do because now what we're going to do today is really set up some vocabulary changes to get into the next homework video where I'm going to now apply energy to our phases. And so we're just going to set up today with a little bit of vocabulary changes, and then we'll apply this energy thing for next homework. Ready? So phases of matter as they exist, of course, at standard temperature and pressure. And there's that big freak out thing, right? Like in math, we have the fraction freak out. And it seems so far this year that we have gotten a little bit stumbled on standard temperature and pressure. I don't want you to get upset about this. It's on table A in the reference tables. It is 0 degrees Celsius in 1 atmosphere, standard temperature and pressure. And the reason why we do that is because we want to be able to make sense, apples to apples, oranges to oranges. Whether I'm dealing with solids in the United States or if I'm dealing with solids in England or in South Africa, we want to be able to have a systematic way where it's the same for everybody. That is standard temperature and pressure. And like I told you in class, it really just refers to normal conditions. So at normal conditions, right, solid, liquid, gas, and also plasma, which we're not going to use, and there's a little aqueous. What I want you to pay attention to right here is this notation. So now we can define this little s, this little L, and the little G. You will see that on paper to designate that that particular thing is a solid, a liquid, or a gas. We don't have anything for plasma, and guess what? We're not even going to use it in Regents chemistry, so that's a good thing. Now, aqueous is a little bit different. Now, it's not actually a phase, but we do need to designate a lot of times that something is dissolved specifically in water, be it a gas or a solid. If it's dissolved in water, aqua, right, we can call it aqueous, and that is designated by that little AQ. Okay, so picture on the right hand side. This is a very good kind of pictogram of how we are going to change phases and, importantly, what the atoms look like in each phase. So first, let's apply our notations because solid is little s, right? And gas down here is little g, and liquid here is little l. Okay, good. Now, look at all these other vocabulary words we have to worry about. So let's deal with solids and liquids first. So as I go from solid to liquid, we can call that solidify. We also might have heard of, right, freezing. The water's turning into ice. If I go from solid to liquid, that's melting. There's another term that we need to throw in there for that, and that is called fusion. Underline that one. That one's going to be a tricky one that we're going to have to remember. All right, let's go down here. Gas and liquid. As I go from liquid to gas, we vaporize, okay? Or I become a vapor. As I go from gas to liquid, and I know you've done this, right? It's kind of cold outside, and there's a screen door with a glass, and you're blowing on it, right? And it fogs up, and you write your name in there. I know you've done it. That's condensation. So that's when I go from gas to liquid, and that's just the water vapor of your breath, right? Condensing into liquid water right there on the glass. But it's fun. I know we've done it. All right, here's where the two new vocabulary terms that are going to really possibly be a trip up for us are, and of course they're going to be on the test, and that the Regents is going to ask them because these are the new ones. Hey, are you paying attention, right? So as I go from gas directly into a solid, that is called deposition. Okay, new one. From gas directly into solid, I'm going to skip that whole liquid phase. Not very many things can do this, but it is possible. And if I go directly from a solid to a gas, I have sublimed. Okay, or sublimation would be the verb, right? And there's a very common example we would use for that, and that'd be CO2. Solid CO2, dry ice, it's a solid, and as it goes to a change phase, it creates the fog on stage. It's going directly into a gas. Never liquid carbon dioxide goes from solid to gas. So it's going to be the most often time you'll see that is with carbon dioxide. All right, heavy notes. We're going to describe what's going on with solids, liquids, and gases. Let's start with solid. We'll work our way down. What's going on at the atomic level? Solids are going to have a definite shape. They're going to have a definite volume. I can measure both. And their particle movement is basically fixed. One atom in a solid is going to hang out in a fixed position to its neighboring atom. Do they have movement? Yes, but the movement is technically vibration. Okay, they have a very high density because they're all packed in nice and tight together, and because they're so close, they can have a very strong intermolecular force. Now this pictogram on the bottom is kind of okay, but I would like you to put a new one on for me because I want to see the shape of your container, but I want to see your particles touching, and I don't want to see them touching the walls. Okay, because now that implies that I'm not taking up the shape of my container and I'm a solid thing sitting there, and this space on either side here, that space helps me understand that that piece is a solid, okay, and that those atoms are rigid and hooked on next to each other. Okay, all right, liquid. As we moved up the spectrum of adding energy, it's going to take the shape of my container, and it has a definite volume. Okay, now if my coffee cup is half full, is it going to take the entire shape of my container though? No, because these particles are still touching. So they're able to rotate around each other now. They're able to move, but they do stay touching. So that gives them a fairly high density, but of course a smaller density than solids. Okay, but I still can't compress them, which is a good thing. That's how your brakes work actually in the car. Because they are still touching, I have a strong intermolecular force. And again, I want to just redo this pictogram one little bit. I want to show that not only are my atoms touching, now I want them to go to the walls. Okay, because when I put coffee in my cup, there's no way it doesn't touch the edges, right? Or if you ever get a hot cocoa, you ever seen any room in between the edge of the liquid and the side of your container? No. And the other thing I want to do is I don't want to fill it all the way to the top. I want to leave some space because this shows me that I have my definite volume, but that volume is limited, if you will, by how much liquid I actually have. And it's going to make a little bit more sense when we get to this last pictogram of gases. So let's add a little bit more energy. Now the gas is going to take the shape of my container, and this is true. So think of the air in the room. Is there a nook or cranny in my room where there isn't air? No, it's going to go everywhere. So it's going to take up the shape of my entire container, and I want to make sure that that's a piece that we put into our pictogram. Again, the volume. The volume is going to take the entire volume of my containers. So I look around the room real quick, there's a lot of air in here. But if I had some way to grab onto it and squish it, I could take that same amount of air, the exact same amount of particles, and put it in a slightly smaller container. So the size of the container with a gas now is what's going to limit how or define its volume. Okay. The particles are completely free to move. They have lots and lots of energy. Think of that 5-year-old all hopped up on sugar. They're cruising all around. They have very low density because of this distance in between them. Can I squish them closer together? Absolutely. And because they are so far apart, I now have weak intermolecular forces. Now this pictogram I'm very okay with. I like that the particles are separated, and I want to see that there's some on the top. I want to see them like that. I want to see them kind of touch this wall and touch this wall and touch this wall. I want to see them all over, and I want to see space. And you notice that these little lines here are kind of implying that they are moving around. So another great analogy with these guys, when I'm in a gas, you can think of a pool table or a billiards table where you just struck the cue ball and it hit and you broke the rack, and there's pool balls going everywhere in straight line motion, and everybody's going all over the place. That's kind of exactly what's actually happening here. And there's energy involved in there. And so you know that next notes, we're going to get into that energy and what's going on. So now we can differentiate between the phases of matter at the atomic level, what's actually happening with our atoms and our molecules. There is a quiz for you to do titled Phases of Matter. So you do that, and then we will be all set. Thank you guys. See you in class.